All right. So in today's session, we are just trying to revise chemistry one that you guys wrote. Okay. So that's what we are trying to revise here. Okay, so we'll go straight into the question. Okay, so the paper I'm using it as answered, so I'll be explaining how they were coming up with these answers. Okay, so if you have a question, you're free to ask. Okay, don't hold yourself. Okay, so question one, they're saying choose the correct statement about a measurement there. That's the question. Choose the correct statement about a measurement. Okay. So when you talk about a measurement, either in physics or in chemistry, it's just something that has a magnitude and a unit. That's what a measurement is. Okay. So for example, if we are measuring length, we would say maybe 5 meters. Okay. So this is a measurement. Why? Because it has a number there, which is the magnitude, and it has a unit. Okay. So it tells you that it's a measurement of something. Okay, because it has a unit there. So let's say, for example, we only had 2. This 2 is not a measurement, okay? Because it's not giving us any information that they are measuring something. It's just 2. Or maybe if I write a number in this way, maybe I say 7.1 multiplied by 10, the power minus 2. Okay. So this number here, without any unit, it's not telling us anything. It's just telling us that it's a number. But immediately you add, let's say this is maybe kgs. Okay. So you would have a number there with a unit. Okay. So this number here is indicating how much of these kgs we have. So it becomes a unit. So a unit, I mean a measurement. So a measurement always has to have a number and a unit all the time. That's when it can become a measurement, okay? So you can see there from the answers that they chose option B there, because that's the correct answer there. A measurement should always have a number and a unit all the time, okay? If it only has a number and a prefix, then it's not a measurement. All right, so that's why they chose B there as our answer. And then they're saying indicate the uncertainty digit in the measurement recorded as 160.0 meters. Okay, so the uncertainty digit is always the digit at the end of a number. So if, for example, let me give another example. I have 140.07, and then they ask you, give us the uncertainty digit here. It's just this number at the end. That's the uncertainty digit here. Okay. For example, we had 20.11. Then I say 8. Say, what is the uncertainty number here? Okay, the uncertainty number is simply this 8 there. So in this number here that we've been given, which is 160, we can see that the last number there is just 0, right? So the last number always indicates the uncertainty of the digits. Okay, no wonder here they put 0 as our answer. Okay, I hope you've gotten that. Okay, let's go to number 3. Number 3, what are they saying? They are saying question 3, 4, 5 are based on the table below. Okay, and then in this table, we have a number of protons in the nucleus, number of neutrons in the nucleus, number of electrons, mass number, atomic number, and then you have the net charge there. So before you answer this question, you have to know the definition of all these terms here. Okay, so number of protons, we know that it's just the number of protons. Number of neutrons, we just know it's the number of neutrons. And we know that protons have a what? A positive charge, right? Then these neutrons have a negative charge. Number of electrons, oh, no. The neutrons have a neutral charge. They don't have any charge, yeah. The neutrons don't have any charge, and then the electrons have a minus charge, okay? And then what is the mass number? The mass number is simply, okay, adding your protons to the neutrons. That's the mass number, guys. If I add my number of neutrons here to the number of protons there, then I get my mass number. Okay, so this mass number is just protons plus neutrons, okay, to give you the mass number. And then the atomic number is just the number of protons. So when they say number of protons or they say atomic number, they mean the same thing. And then the last column there is net charge. So this net charge. Yeah, someone has a question? Hello?
I'm saying I don't know if I'm, but I'm able. Yes, I'm able to do this. I don't know if I want.
I can't get you. Can you repeat? They're saying what?
I was unable to the screen, so I don't know if I'm the one. Am I able to the screen?
You can't see my screen.
No.
Okay, is that the case with everyone or it's just her? Someone to confirm? All of you guys can't see my screen? Hello? The network, right? Yeah, so try to maybe log out and then you log back in. Okay. All right, so I was saying atomic number is the same as number of protons, and then the net charge there indicates either you have extra electrons or you have less electrons, okay? So if you have extra electrons, then the charge will be negative there. And if you have fewer electrons, the charge will be positive, right? Okay. So, but we know that in a neutral atom, we know that the number of electrons should always equal the number of protons. Okay. Yeah. So let's try to fill in those blank boxes there. Let's try to see if we fill in those blank boxes. Okay. So using the information that we've been given there, okay. So these are the number of electrons there. And then this is the mass number, atomic number. We have all those things there. Okay. So looking at this electron number there, the number of electrons there, and this charge, we can get some information from there. Okay. Because we said the net charge indicate either an excess of electrons or a deficit, right? So if it's negative, then it means that there's an extra 2 electrons that have been added to this atom, okay, or to this isotope, or yeah. So if I have 36 electrons there and my charge there is negative, what does it mean? Okay, what does it mean? It means that this isotope originally it had 34 electrons, okay? And when it had 34 electrons, the charge was 0. And then it gained an extra 2 electrons, and that's how the charge has become a what? A -2 there, okay? So from this, if we want to find the atomic number there, we'll just say the atomic number is equal to the original number of electrons, okay? Because in a neutral atom, the number of electrons, the number of protons, they should be equal, okay? So the number of protons here should be 34. And then even the atomic number there, because we said number of protons, atomic number is just the same, should be 34 here, okay? How are we getting that 34? We're just saying 36 minus this minus 2 there, right? So we are getting a 54 there. And then how do you find the number of neutrons? Okay, so the number of neutrons, remember we said the mass number, is just the sum of, okay, the mass number is just the sum of the protons plus the neutrons, right? Okay, but we know the number of protons that we have. So how are we going to find this number of neutrons? We are going to say the mass number, which is this one here. The mass number 79 is equals to the number of protons, which we found it's 34, plus the number of neutrons. Neutrons we don't know. Okay, so we'll put n. And then we solve for n. So n will be equals to 79 minus 34. Okay, so this will give you what? 9 minus 4, it will be 5. 7 minus 3, it will be 4. Okay, so the number of neutrons there will be 45. So we've filled in all the boxes there, and then we can proceed to answer our questions now, right? You can proceed to answer our questions now. Okay. So the first question there is, what is the atomic number? So the atomic number, you found it's 34. Wonder here they put 34 there, you can see. And then the follow-up question, how many neutrons are in this isotope? We found it was 45 there. So here, no wonder they put that 45. And then the other one is how many protons? Okay, so protons is the same as the atomic number. So 34, it means even the protons there you have the 34. No wonder the answer here is A. Okay, then we move to question 6 now. So if you have any question, just feel free to stop me. Okay, so question 6, they are saying the direction formula is given by M1 V1 is equals to M2 V2. And then they are saying, what does the letter M mean in this formula? Okay, so we know that this M here is just the concentration in what? In moles, right? And it has the special name molarity. Okay, molarity. So the answer there should be molarity with the R here. Okay, with the R there. But here you can see that we have a molarity with the L. So this one is not the answer there. No wonder here they're saying none of the above choices is correct. Okay, because the correct answer is this one, molarity. This molarity here means something else. It means the concentration in kilograms, right? That's molarity here. Yeah, so no wonder they put this as our answer. And then question 7. Okay, so I don't know how to pronounce this word, so I'll skip it. But this thing is a relatively rare pink to purple mineral with a complex mineral formula. Okay, so I've been given a mineral formula there. You can see it's very complex because there's a lot of elements in it, right? So this is what the formula there, a complex formula that have been given. And then they're saying it is valued in the gemstone and jewelry industry for its unique color and appearance. Okay, all this is it's not even necessary for the question. So the question now starts from here. They're saying an analysis of the mineral revealed that it has 0.012 moles of silicon. And then the question now is determine the moles of oxygen atoms. Okay, so how can we determine the moles of oxygen atom? We just have to get the mole ratio of the silicon to the oxygen. So we'll get the mole ratio of this silicon to the what? To the oxygen. So from the formula there, we can see that when we have 12 silicon, we have 30 what? Oxygen. Okay. And then in the question, we've been given 0.012. So you put your 0.012 here, and then you are going to say is equals to X moles for the oxygen. And then you just simply cross multiply, right? So it means here I have 12X multiplied by 0.012 multiplied by 30 there. Okay, and then here I'll divide both sides by 12. So if I divide both sides by 12, what am I getting? Let me check on my calculator. But you can confirm the answer on your calculator as well. Okay, so when I multiply, my calculator is giving me 0.030 moles. Okay, and these will be the moles of what? The oxygen there. Okay, so no wonder they put that as our answer there. Okay, so you just simply have to get the mole ratio from there and then compare it with the moles of silicon that you'll be given there to find the unknown moles of the oxygen. Okay, I hope we are good. Okay, let's go to number 7. Okay, so number 8, I mean. Okay, number 8, they're saying the concentration of iron in 130 grams of powdered milk sample was determined to be 3.80 micrograms. Okay, and then they're saying determine the concentration of this iron in parts per million. Okay, so parts per million, we know that we're just simply multiplying the concentration by 1 million, right? That's parts per million. It's like, for example, when they say percentage, it means whatever fraction that you have, and then you want to find the percent, you just have simply multiply by 100, right? Okay. So that percentage, it is also known as parts per hundreds. Okay, parts per hundred, meaning you are multiplying whatever fraction that you have with 100 to find the percentage. Now, when we're talking about parts per million, it means I can have a fraction here. Let me say A over B, and then I want to change this into parts per million. It means I'll just multiply with the 1 million, right? Whatever value I'm going to find here will be my parts per million. Okay, so here we have the concept. We have the concentration of iron in 130 grams of powdered milk to be this guy here. Okay, so how are we going to find that fraction or that concentration? We're simply going to divide the mass of the iron, okay, divided by the mass of the sample. Okay, but before we divide these two masses, we can see that this is in grams and this is in micrograms. So we have to change them into a common unit. It's either we change them both to micrograms or we change them both to grams, and then we can multiply by the 1 million. Okay, so I'll choose to change this number into grams. So I have 3.80 and then micrograms there. Okay. So how do I convert this guy into grams? Okay. So if you remember on your prefix table there, micro is just 10 to the power minus 6, right? Micro is 10 to the power minus 6. So it means for me to convert this into grams, I'm just going to say 3.8 multiplied by 10 to the power minus 6. And then this will change from my micrograms here, it will become gram. Okay? So you have to know those prefixes on your metric table. You have to know them. You have to know what nano means, what pico means, what micro means, just like that, okay? So this micro here simply means 10 to the power minus 6, okay? So this is the mass in grams, okay? And then we're dividing this mass in grams with this 130, and then we are multiplying by 1 million. So that's what we are going to do. So we are going to say 3.8 multiplied by 10 to the power minus 6 over 130, and then multiplied by 10 to the power 6, okay? So 1 million is the same as 10 to the power 6, guys. So when you multiply this on your calculator, what are you going to get? Okay, so here we can see that we have 10 to the power minus 6 and 10 to the power 6. So it means if we apply the rules of indices here, we can say 10 becomes the common base, and then we add minus 6 to the 6 there. It means we're going to have 10 to the power 0, right? And 10 to the power 0 is just 1. So this is just simply 3.8 divided by 130. So 3.8 divided by 130, what does it give you? Okay, what does it give you? Okay, so 3.8 divided by 130, it's giving me this number, 0.0, yeah, what have I written? Okay, yeah, it's giving me 0.029. Okay, I was saying it gives me 0.0292, and then 30, and then the number goes on like that. So you can just round off this number to maybe 4 decimal places like they did, so it will be 0.0292 like that. Okay, so you can see that this will be our parts per million. No wonder here they put it as our answer there. So that's how they came up with this value. Okay. So you first convert this to grams, then divide it by the 130 multiplied by parts per million, which is just 1 million. And 1 million is the same as 10 to the power 6 there. Okay, we go to number 9. Okay, so question 9 says what? They're saying which law, okay, they're saying which law expresses the link between the solubility of the gas and the pressure. Okay, so the law that associates the solubility of the gas and the pressure is just simply okay. So the law that expresses the link between solubility of the gas and the pressure is simply this law here that we call as the Henry law. Okay, and the Henry law is given by this formula. Okay, I don't know if you know it, but I hope you do, because it's coming in the exam, whether you want it or not. Questions about this law, don't miss. Okay. So it's given by the formula C, okay? Given by the formula C is equals to K multiplied by P, okay? This C here, okay, represents the concentration of the gas. That's the C. So concentration of the gas, that's our C. And then this K here represents the what? Represents the Henry's law constant. Okay, so Henry's law constant. That's what it represents. And then this P here, we all know that it represents the what? The pressure, right? It represents the pressure. Or okay, be specific and say the partial pressure. Okay. The partial pressure of the gas. Okay. So we can read now the question again. So we are saying which law expresses the link between the solubility of the gas and the pressure. Okay, so this is the law here, the Henry's law, and it's given by this formula here. Okay, yeah. Okay, let's go to question 10 now. Okay, question 10, they're saying the measured values were recorded as 18.6 meters, 18.5 meters, 8.5 meters, and 38.4 meters. And then they're saying the true value was 28.5 meters. Which of the following is the correct statement? Okay, which of the following is the correct statement? Okay, so here you have to know the definition first of what precision is, what accuracy is, what is a random value, and what is a systematic. Did I say random value? I meant to say random error, and what is a systematic error. Okay, so we know that precision is just how close the measurements are, right? And then accuracy is how close a measured measurement is to the true value. Okay, so we can see here that we have 18, 18, 38, 38, and the true value is 28. So meaning this one was not even accurate. It was not accurate. So the debate about accuracy, we can just forget it. And then let's talk about precision now. So precision, we're saying how close these measured values are to each other, right? So you can see we have 18, 18, 38, 38. So meaning these measurements here are not precise, right? Okay. And then what caused these measurements to be not precise? Okay. That's where now the random error and the systematic error comes in. So when we say random error, it's just an error that occurs in any direction, okay? So from the true value, you can have a value increasing or decreasing. That will be a random error. If it's a systematic error, it will it will be off from the true value in one direction. Okay, let's say if the true value is 28.5, right? And then those measurements are affected by systematic error. It means all the measurements that I'm going to find are going to be in one direction, maybe to be 33, another one will be 35, another one will be 36. You can see that they are going in the same direction like that. But if it's a random error, you have some value that will be less than this number and some value that will be greater than this number, which is our case that we have here. We can see that from the true value, we have values that are less than the true value, which are these my 18, and we have values that are greater than this value, which are these 38, right? Okay, so what can we conclude now from this? We can see that these measurements, one, they are not precise, and they are affected by what? Random error, because some of them are smaller than true value, then the other one are bigger, right? Okay, so that makes A the best answer there. That makes A the best answer. Why? Because it's addressing all the two facts that we have found here. Okay, so we can see that these measurements are not precise, so we say they were imprecise, and then they were affected by what? Random error. Okay, what is random error? An error that occurs in any direction. Decreasing, increasing, that's a random error. Systematic error, it will be an error that will go in one direction. Either it will just be decreasing or it will only be increasing. So know the difference, right? Okay, so that's number 10. That's why they chose A there as our answer. And then number 11, they're saying choose the correct statement. Okay, so what statement do we have? Okay, so this is about the percentage yield. So percentage yield is just equals to what? Actual yield over theoretical yield multiplied by what? 100. Okay, so now let's read these statements here and choose which one is correct. So they're saying theoretical yield is always achieved in comparison to the actual yield. Okay, so this is a false statement. Okay, because when you're trying to run a chemical reaction, you always get something out of that chemical reaction. That something is what we are calling as the actual yield. So the actual yield is always achieved in a chemical reaction. But the theoretical yield, it's very difficult for you to achieve the theoretical yield. No wonder these most of these chemical equations, they're not 100% effective. Why? Because the theoretical yield cannot be achieved, right? Cannot be achieved. Yeah. Or if it's achieved, then you have to put in a lot of measures. Okay. So this statement on A, because they're saying theoretical yield is always achieved. This is false. Theoretical yield is not always achieved, but the actual one is the one that is easily achieved. And then here they're saying the actual yield is rarely. So the word rarely makes this statement false, because this actual yield is always achieved, right? Okay, so our answer there will be C, which says the theoretical yield is rarely achieved, yes, in comparison to the actual yield, which is always achieved, right? So the best answer there was C. Okay, and then here they're saying determine the vapor pressure over a solution if the vapor pressure of a pure water at 39.8 degrees Celsius is 44.72, and the mole fraction of the solution is 0.888. Okay. Have I skipped a question here? No, I haven't. Okay. So this question here on number 12 here, we answer it using this law here, which is on A there. The law that is known as Raoult's law. Okay. So Raoult's law is given by this formula. We're saying the pressure, okay, of the solvent over the pure solvent is equals to, okay, is equals to the mole fraction, which is given by X, multiplied by the pressure of the pure solvent. Okay, so pressure of pure solvent here. Okay, so pressure of the solvent over a solution here is given by the mole fraction multiplied by the pressure of the pure solvent. Okay, so here you can see that determine the vapor pressure over a solution if the vapor pressure of the pure water, this is what we're referring to as pure solvent, at these degrees is this. So meaning this guy here, the pressure of the pure solvent is just 44.7, and then the mole fraction there, they've given us that. So now we are finding the pressure of the solvent over a solution, right? So I'm going to write P solvent over, I'll just write SO solvent over is equals to the mole fraction, which is 0.888 multiplied by the pressure of the pure water, which is 44.7. So what do I get here? Let me check my calculator. Okay, so 0.88 multiplied by 44.7. You're going to get 39.69. Okay, so this is what you're going to get as your pressure. And we can see clearly that on the options there, it's not there, right? There's no 39.69 here. No wonder they chose D, the correct answer here, which says none of the above. Okay. Hope that is clear. And then let's look at question 13. Okay. And erase this. Okay, so question 13 now, it says what? They're saying in an osmotic pressure experiment, the moles of a certain protein were determined as 6.03 multiplied by 10 to the power 8 moles. And then the mass of that same protein used in the experiment was 1.00 times 10 to the power 3 grams. Determine the molar mass of the protein. Yeah, so this is very simple, guys, right? We know that moles are equals to what? Mass over molar mass. So in this question, we've been given the mass, we've also been given the moles. Now we are finding the molar mass. So molar mass is equals to what? If I make the mm to be the subject of the formula, just be mass over the moles, right? So is equals to the moles there. They'll be what? Okay, the moles, they'll be 6.03 multiplied by 10 multiplied by 10 to the power minus 8. Okay, so 10 to the power minus 8 there. And then we are dividing this number by 1.00 multiplied by 10 to the power minus 3. Okay, so what do I get when I punch this into my calculator? Okay, so 6.03 multiplied by 10 to the power minus 8 divided by, okay, divided by 1 multiplied by 10 to the power minus 3. Minus 3. Okay. Let me put brackets here. Okay. Okay. Okay, so after I divide here, what is it giving me? Okay. Okay, so here I did the opposite, guys. No wonder I'm finding another answer. I put the moles on top and then the mass down. The mass should be up there, the moles should be down, according to the formula here, right? So mass and then divided by the moles. So I did the opposite there. I wanted it was giving me another answer. Let me correct that. Okay, so we are saying mass over moles, right? So what is the mass? The mass is this. So this value is the one that should be on top there. And then divided by 6 0.03 multiplied by 10 to the power minus 8. Okay, let me see now what I get when I punch this. Okay. Okay, so I'm getting 1.66 multiplied by 10 to the power 4 there. Okay, and the units will be grams per mole. So you can see that this is the exact answer that they put there, which was B. Okay, so this is how they got it. Okay, let's go to question 14, which is the last question from the multiple choice section. Okay. Okay, so question 14, they're saying what terminology is used to describe the substance that finishes first in a chemical reaction? Okay, we all know that the answer is limiting reactant, right? Or limiting reagent, whatever. But you can see that on the options, there is no limiting reactant. No wonder the answer there was none of the above. Okay, yeah. All right, then we go to section B. Go to section B, okay? So I'll simply explain what they are doing here. If you have any question, please ask. Okay, so to move fast, I'll simply explain what they do here. I don't want to start writing again. So they're saying determine the empirical formula of a compound containing 29.09% of sodium, 40.55% of sulfur, and 30.36% of oxygen. Okay, and then they're saying follow the order as indicated, meaning we are starting with sodium, then sulfur, okay, and then oxygen. So we are going in that way. Okay, so what's the first thing when you're trying to find the empirical formula? So you write your elements there on top. My sulfur is my sodium, my sulfur, and then my oxygen. Okay, and then the next thing is to write my masses there. Okay, so this percentage here, because we assume that it's from 100-gram sample, so the percent becomes the mass. Okay, so they write 29.09 is the same as 29.09 grams. No wonder here they put the mass of sodium to be the 29.09, mass of sulfur to be 40.55, mass of oxygen to be 30.36 grams. Okay, then after you put these masses, what do? You divide each and every of those masses by the molar mass of that element. Okay, so from the periodic table, we know that the molar mass of sodium is just 23. So no wonder here they are dividing that mass by the 23. And then for the sulfur, we know that it's 32 point something there. Okay, 32 point something about that value. So we are dividing this 40 by a 32 there. And then for the oxygen, we are dividing this mass. What is the molar mass of oxygen? Okay, the molar mass of oxygen is just 16, right? Okay, so we can see here they are dividing by 16. So when you divide mass by the molar mass, what do you get? You get the moles, right? Okay, so these are the moles that they got here. So these are the moles of sodium, moles of sulfur, and then you have the moles of oxygen there. Okay, so once you get these moles, what do? You look for the smallest value among these moles, and then you divide all these moles by that same value. Okay, so this is 1.2, 1.8. This one we can forget. 1.2648, and then this is 1.2644. So you see that this guy here is the smallest, right? So we are going to divide all these values here by the smallest number of moles. So this one, you divide it by this value, you're going to get 1. This guy divided by itself, definitely you're going to get 1. Then this guy here, if I divide it by this number, I was getting 1.5 there. Okay, so now here, that's where the trick is. Someone may be tempted to say 1.5. Let me just round it off. It comes to, right? And then our formula will just be sodium 1, sulfur 1, and then oxygen 2, right? That's what they may think. But no, So let me show you the rules for rounding. Okay. So when you're finding the empirical formula, we follow rules when rounding off. So you can only round off if a value is below, okay? If a value is below x.2. Let's say I have a value such as, let me say 5.1, okay? Or 2.1. These values here I can round off, okay? And then I can also round off if I have a value that is above x.8, okay? If I have a value above x.8, I can round off. So let me say I had 2.9. This one I can round off, okay? 3.9. This one I can round off, okay? So you can only round off if I have a value that is above x.8 or below x.2. This x here, guys, represents any number. You can put any number here. So as long as this number that comes after this point is above the 2, I mean it's below the 2, you can round off. If this value is above the 8, you can round off. But if you have a value that is between x.2 all the way to x.8, these values that are in between here, you can't round off, okay? You can't round off. So let's say, for example, at 3.4. This 3.4, you can never should you ever round it off, okay? You don't round off such. For example, I have 2.5. Don't round off. 1.5, don't round off, because these values are between the x.2 and the x.8. So what do you do to these values? Okay, what do you do to these values? You look for a number, okay? You look for a number such that when you multiply this number, they can either give you a number that can be rounded off in this form, that will have a 0.9 or a 0.1, or they can directly give you a whole number, right? Okay. So for example, this 2.5, we know we can just multiply it by 2 and it will become 5. Even this 1.5 can multiply it by 2, become 3. This one here, we can multiply it by what? If we multiply it by 2, we are going to get 6.8. 6.8, you cannot round it off because it's that value there. So you look for another number again, you multiply until you get something that has a 2.9 or a 5.1 there. So if I multiply this number again by 2, what am I going to get? Okay, so 6.8 multiplied by 2, I would get 13.6. So 13.6, I can't round it off. So I continue trying until I find such numbers. So now going back to the question here, we're at 1.5 here. 1.5 is between that x.2 and the x.8, right? So we can't round it off, right? We can't round it off. So we are going to look for a number such that when you multiply this number, it becomes a whole number or a number that we can round off. Okay, so a good number here to multiply this is just 2. So when you multiply this number by 2, it means you also multiply this one, you also multiply this one. I wonder here, you are seeing that 2. So if you're asking yourself, where is that 2 coming from? You've known now. So you multiply everything by 2, you get 2, 2, 2, 3. So it means our empirical formula will just be sodium 2, sulfur 2, and then you have the oxygen 3. Okay, so that's how they got that answer there. Okay, so that's our answer there. Let's go to the other question. Again, I'll explain using the same solutions that they have here. Okay, so here they're saying what now? They're saying how many grams of copper sulfate, and then they have given us its molar mass there, which is the 159.61, are required to prepare a 250 milliliters of 7.03 times 10 to the power minus 3 molar solution. Okay, so if I go to my screen here, what do I have? Okay, I have copper sulfate there with a molar mass of what? 159.61. Okay, grams per mole. Okay, so in this question, what are we trying to find? We're trying to find how many grams. So how many grams we're trying to find mass, right? Okay, so how many grams of these coppers are required to prepare a solution of 250 milliliters multiplied by this molarity? So we can see that from the molarity and the volume, we can find the number of moles, right? Okay. And then those number of moles, we are going to combine them with the molar mass here to find the mass that is required. Okay. So we know the formula for molarity. Molarity is just equals to moles over the solution, over the volume of the solution. So molarity is equals to moles over the volume of the solution. So it's very important to give these formulas. You can see here they are giving them to my marks, right? So you should know the formula. So molarity is equals to moles over volume, and we know this volume has to be in liters. And then here they were supposed to say moles is equals to mass, not moles here on top. Here on top, you're supposed to have mass there. Supposed to have mass. Okay. So moles is equals to mass over molar mass. Okay. So what do we have? We have a concentration there, which is the molarity, and then we have the volume. So we can use this molarity and this volume to find the number of moles. Okay. So from this formula I can write it as moles. Our molarity is equals to moles over volume. But now I want to find my moles. So N will be equals to what? MV, right? Okay, so I put my concentration here, which is my molarity, multiplied by my volume. But remember, the volume has to be in liters, but this one is given in milliliters. So what do we do to turn it into liters? We divide by 1,000. Okay, dividing by 1,000 is the same as multiplying by 10 to the power minus 3 here. Okay, so we have molarity multiplied by volume in liters there. I'm getting these moles as my moles of my copper sulfate there, right? Okay. And then after getting those moles of copper sulfate, I'm just going to combine these moles with the molar mass to find the mass. Okay. So remember the formula is moles is equals to mass over molar mass, right? But we want to find the mass, so it means mass will be equals to moles multiplied by molar mass, right? So let's put our moles and our molar mass into that formula to find our mass. So you can see moles multiplied by my molar mass. So this moles that I'm from finding here multiplied by my molar mass that was given. It's just give me 0.281 grams. Okay, so this is the mass of my copper sulfate that is required there. Okay, so that's how you go about that question. I don't know if I have any questions. Okay, good. No questions. Okay, then the next question they're saying what? In an experiment, a student added 15 milliliters of water to 83.2 milliliters of 1.06 molar solution. Determine the molarity of the solution prepared in this experiment. Okay, so here you simply use M1 V1 is equals to M2 V2, right? Okay, so what is our M1? Our M1 is the concentration that is initially given, which is just 1.06. Okay, and then the volume before the addition of another volume. What was the original volume? That is our V1. So if I go back to this, they're saying they added this amount of water to this amount of volume. So this one here is our V1. Okay, so 83.2 is our V1. So I write 83 here, 0.2 is equals to the molarity 2, which is what we are finding, and then the V2. So how do we get the V2? So if I go back to this, originally add the 83.2 mils, right? Okay, and then to the 83 point, where are my questions now? Okay, originally add 3.2 mils. Okay, and then to this 83.2 mils, they have added 15.5. Okay, so the new volume or the V2 will just be 83.2 plus, okay, 83.2 plus the 15.5. So I'm going to get a 98.7. 98.7. So this will be my V2. So there you can see my M1 is there V1 is there, my M2 is not there, that's what we are finding, but my V2 is there. So your V2 will just be V2 is equals to, multiply this and then divide it by that. Okay, so 1.06 multiplied by 83.2. I'm getting what? I'm getting 88.192 divided by my 98.7. Okay, so what do I get when I divide? Okay, 88.192 divided by 98.7. Okay, so I'm getting 0.89, okay, as my new molarity. Okay, so we can check what they found there. Okay, yeah, you can see that whatever they found is the same. So the M1 is that, V2 is that, M2 is what we are finding. The V2, you add what was added plus the original volume, which is 15.5 plus that, you get that. Okay, then you divide there, you find your unknown, your M2, you're going to find is 0.89. Okay, molarity there. So that's how you solve that question. Okay, what is remaining here? Okay, so this is the other question here now. So question B3, I think it's the last question in this test, I don't know. Okay, so ozone is produced when oxygen molecules are subjected to electrical discharge or the action of cosmic rays in the upper atmosphere. Okay, so the first question there, they're saying calculate the mass of ozone that could theoretically be produced by the conversion of 1.47 grams of oxygen, right? And they have given us the formula there, okay? So the formula, they're saying 3O2, when it's exposed to this electrical discharge, it becomes ozone there with a 3 there, okay? So how are we going to solve this, guys? We're simply going to use the mole ratio, right? Okay, so we have 1.47 grams of the oxygen, right? So we can find the moles of this and then compare it to the moles of that, okay, for us to find the mass of this that was produced. Okay, so let's do that. So how do we calculate the moles here? We have the mass, and we know that the molar mass of oxygen is what? Okay, oxygen, that is the atomic, which means oxygen has got 2. So one oxygen has 16, the other oxygen has 16. So meaning it's 32, right? Okay, so moles will be equals to mass over molar mass there. So what is the mass? 1.47. Then what is the molar mass of a diatomic oxygen there? It's just simply 32. So when I divide that, I'm getting 0.04593 moles. Okay, so these are my moles for the oxygen, right? And then how do I find the mass of this? It means I'll use first the mole ratio to find the moles of ozone. And then after I find the moles of ozone, I'm going to get its molar mass, combine it with the moles to find the mass. Okay, as simple as that. So the mole ratio there, you can see from oxygen to ozone, it's just 3 to 2. Okay, so now I have these moles of oxygen. So I'm going to say 0.045938 to the moles of ozone that we don't know, X. So cross multiply. Okay, so 2 multiplied by this and then divided by 3, it means our X will be equals to what? Equals to 0.03. Confirm these values on your calculator. So 0.030625 moles. So these moles here are for ozone, right? The moles are for ozone. And then we know we can get the molar mass of ozone. So ozone is 023 there. Okay, so 023, what is the molar mass? One oxygen has 16. 16 multiplied by 3, we are going to get 48. So now to find the mass of this ozone, you're just going to say mass is equals to moles multiplied by molar mass. Okay, so what is the value of the moles? 0.036025 multiplied by the molar mass, which will just be 48. Okay, so when you multiply this, what are you going to get? So let me multiply. So 0.030062 multiplied by 48. Okay, I'm getting 1.47 grams on my calculator. Okay, so this will be the mass of the ozone. Okay, so you can see whatever I was doing here is what they were doing here. So they first established their mole ratio there. Okay, then they found the moles of oxygen, which were just this. Okay, then they compared these moles of oxygen to the moles of the ozone there with the mole ratios. You can see 3 and 2 there. They found this to be the moles of ozone. And then you have now to get the molar mass of ozone, which is just 48. So 48 multiplied by this value, I'm getting that as my mass for ozone. Okay, so that's what you do. So this is, remember they said theoretically here. They said what? Theoretically. Okay, so this is the theoretical hue there, or the theoretical mass. Okay, and then what's the next question? They are saying if 0.111 gram of ozone was actually produced. Was actually produced, meaning this one is the actual field or the actual mass, right? The actual mass. What is the percentage yield? Okay, so percentage yield is equals to actual yield over theoretical yield times 100. So actual we have been given is 0.11 divided by, what was the theoretical that we found? 1.47. Okay, then we just simply multiply by 100 there. We're going to get 7.55% as your percentage yield. Okay, so end of test. Oh, you see that? Okay, so I think this was the last question there. I don't know if you have questions for me, guys. Any questions on what we've revised?
It's clear.
Okay, amazing. Okay, so I'll end here. So continue revising for your exams and have a blessed night.
Thank you.
I